Welcome, everyone. Thanks for joining me today, and thanks for finding your way to one of the secret rooms. Unfortunately, I picked up a little bit of a cold here the last few days, so I apologize if my voice is a little rusty. But let's get started. This is a scene from our latest installment in the Hitman game. It's Agent 47 goes to a bank in New York. If you're familiar with the game, you know that there's a victim here somewhere who most likely will have an unfortunate day. But it's also just a regular bank, right? So you have customers, you have tellers, you have security guards restricting access to certain areas. There's a job interview going on somewhere in the building, and another guy getting fired. There's an undercover journalist trying to get the scoop on the bank. There are a couple of IT reporters somewhere who can help fix the Wi-Fi if you break it. And there's a secure vault, of course, it's a bank. And there's an entire floor of stock traders. Now, take a minute to think about what kind of code would you have to write to get all of this running. Done? Good. OK. Now let me tell you that games have to run at a minimum of 30 frames per second. And most games run even faster than that. So in the best case, you have 33 milliseconds to get all of the code you just thought of to run. So games show us that we can get computers to do quite a lot in a very limited time. And yet, we have something like this. In this talk, we'll talk about some of the challenges and techniques of writing high-performance code. And we'll see how we can apply those ideas to the world of C#. My name is Brian Rasmussen. I'm the executive technical producer at IO Interactive in Copenhagen. We make Hitman games. So I think the need to write high-performance code has changed over time. The first computers were really big and slow, and you had to be super careful to get anything done at all, really. And then, luckily for us, I guess, computers became a lot faster, and we started to optimize for programmer productivity. So we built application frameworks that allowed us to build applications faster. We built virtual machines that allowed us to run our code on any machine, really. And of course, these abstractions came at a cost. But the hardware kept getting faster all the time, so it wasn't really a problem. These days, hardware don't really get faster in the same way as it used to. And most of the code runs on either your cell phone or some other battery-powered device, or in the cloud. And slow code uses more power, and that drains the batteries faster, and it makes your cloud bill go up. So to put it bluntly, slow code costs money. How much money are we talking about? Well, Amazon claims that every 100 milliseconds costs them 1% in sales. In 2017, they reported a revenue of close to $180 billion. Now, these numbers might be a little, I'm not going to break down the numbers, but it seemed like there's some room for spending money on improving performance, at least at Amazon. And to do that, you have to think about how your software interacts with the hardware. Regardless of the abstractions we choose, the frameworks we use, and all of that, hardware is still what runs your code. Understanding how hardware and software interacts is pivotal to understanding performance and optimizing your code. So in this talk, we'll look at how can we optimize, how can we understand .NET code and how it interacts with the hardware. And we'll look at what we can do to make code run faster. Specifically, we'll look at CPU-bound problems, and only CPU-bound problems. If you have I/O bottlenecks, you should address those first. If you don't address those, then all of this will be for nothing. So to get us all on the same page, let's start by looking at a super simplified CPU. This is probably not going to help you land a job at Intel, but hopefully it can provide a useful context for what we'll talk about today. So to run code, the CPU goes through a number of phases that could look something like this, at least in the simplified version. So first we read an instruction, we read the data, then we actually do the work associated with the instruction, and finally, we can write back the data if there's any. Now, then we do the whole thing again for the next instruction, and so on and so forth. So we saw that the CPU has different phases that it goes through when running code. And in order to keep all of those phases active all the time, we process instructions in parallel in something we call pipelining. So here we fetch the first instruction, And then we read the data, and while we do that, we start fetching the next instruction as well. And then we execute the first instruction, and at the same time, we're reading the data for the second instruction, and at the same time, we're fetching the third instruction. This keeps all of the different phases of the CPU busy, and it improves performance. Now, pipelining works great if your code is sequential. What happens if the code branches? In this situation, we have a branch, right? We can either go to step 3 or step 4, but we won't know until we've actually completed step 2. So how does the CPU determine what instructions to start fetching? It guesses. And it might be right or it might be wrong. So let's look at what happens in both cases. Let's say that we correctly guessed that there will be no jump. So we start processing the instruction in step 3. At this point, we know the outcome of the comparison, and we know that we were right. We guessed correctly. So in this case, we get the full benefit of the pipelining because we were able to predict the code we needed to run. On the other hand, if the guess was incorrect, we started to process the instruction in step 3, found out that this was not the right instruction, so we had to throw away everything we just did and go back and start from scratch with step 4. That's unfortunate, but the net effect here is still that pipelining speeds up everything. And obviously, the more we are able to guess correctly, the better we'll do. So we saw that the CPU has to read both instructions and data before we can do anything. Unfortunately, memory is a major bottleneck here. It's really, really slow compared to what the CPU can do. So to address that, all CPUs have caches, and caches are tiny but super fast storage unit that can be used to reduce the latency. So if we want to read some data, we first check if it's available in the cache, and if it is, we're good. If it's not, then we have to read it from memory. And memory is typically 20 to 25 times slower than your fastest cache. So that's a huge overhead. And unfortunately, it's a price we have to pay every now and then because the caches are small. But it turns out that we very often need data and code in sequence. So we can use that to help optimize how we use the cache. So if we need some data, we're probably going to need the data right next to it. And if we do that, we can populate the cache. So we get the data we need. Now the cache is populated with some data that we are likely going to need. If we do need that data, we can read it from the much faster cache, which is a great thing. So the more we can make sure that the cache contains the data that we need, the faster our code will run. So these days, CPUs have multiple cores, and they each have their own caches. That means that data will be duplicated, in some cases, across the caches. As long as the cores are just reading from this cache, it's not a problem. All of the cores, really, can get the benefit of the cache reads. But now suppose that, what happens if one of the cores actually want to write this data? If this is the only core that has this copy, it will just write it to the cache and it'll be fine. But if multiple cores share this specific data, the CPU has to do extra work. So in order to maintain that consistent view of this data. So if that happens, the CPU will actually have to flush the data back to memory. And the other CPU, if it needs that data again, will have to refresh its cache from that memory. And obviously, there's the additional cost of doing so. So the more we can avoid this situation, the better we do. So now that we have a basic understanding of the hardware, let's look at some cases. These are the 4 topics that I'll cover today. All of the samples are .NET Core 3.0, and I'm using the benchmark.net library, which is an excellent library for doing micro benchmarks. There are a whole host of problems that you can encounter if you try to do your own benchmarks. So don't roll your own library, just use this. It's awesome, and it's very thorough. It'll do all the work you need to get proper numbers. Unfortunately, because it's so thorough, it's also somewhat slow. Some of the tests that I have in this takes minutes or even tens of minutes to run to get the results. So I'm not going to bore you with looking at a prompt doing absolutely nothing for tens of minutes. All the code is available on GitHub, though. So if you want to try this out and see how it works on your hardware, you can go and do so. What about garbage collection? If you've been to any .NET performance talks, you know about garbage collection. And it is hugely important, and I'm not going to talk about it. but it is important. The reason I'm not going to talk about it is because most game engines these days are written in native code, and in native code you handle memory allocations very differently than what you do in .NET. So there's very little we can lift from that world and apply to the world of .NET. So it is important. If you want to optimize it, you know, the short version is there. Don't allocate anything. You'll be fine. OK, so examples. Let's say we have this simple example. We have a matrix of numbers, and we can model that as a two-dimensional array of rows and columns, just as shown here. Typically, when we have a data structure like this, we want to go through each of the elements at some point. And we can do so by column or by row. And the code is almost identical, right? It's just we swap the two loops. But the performance is very different between the two. The hardware has no notion of a matrix. It just knows about data, and it's all linear. So as we saw, the CPU reads data in these little chunks called cache lines. And when we read by row, we'll read a cache line, take the first element and use that, and then we'll take the next element from the cache line, and so on and so forth. So we get maximum benefit from the caching in this case. If we read by column, we'll read a cache line again, because it wasn't in the cache in the first place. We'll take one element, throw away the rest, and go read another cache line. Because it's so expensive to hit memory, this turns out to be a big difference. In this example, a matrix of 1,000 by 1,000 elements, we can do the same amount of work in 60% of the time. For the larger matrix in this case, we can do the same work in just 15% of the time. If you could optimize your workday in a similar fashion, you could get 8 hours of work done in just about an hour and 15 minutes. I'll take that any day. This is a trivial example, right? But spotting issues like that in real code can be very challenging. If I run this through the profiler, I get the following. So Visual Studio correctly tells me that column first takes a lot longer to run than the row first. That's good. So far, so good. But if you look at the breakdown of what Visual Studio believes where the time is spent in this code, you'll see that for some reason it believes that increment in x suddenly takes 80% of the time. Does that make sense to you? Can you optimize that? What would you do, right? That makes no sense at all. That's not the case. Maybe it generated very different code for your different functions. So .NET Benchmark.net has this nice feature that you can annotate any test class, and it'll output the JIT compiled code for that test. So we can easily get the actual machine instruction here for the two methods. And I'm not going to walk you through all of it, but I've highlighted the differences. And you can see, other than the name, it's really just how the loops are handled here, just like in the C# code. So if we knew absolutely nothing about caches, we would be very pressed to find out why this code actually runs slower in one case than the other. So think about caches when you write your code. Accessing memory is super slow, and the more data you can read from the cache, the better. Think about how your code accesses your data and optimize for cache utilization. Keep in mind that the tools are not always useful here. Data-oriented design is a big thing in game programming these days. I won't be able to do it justice, but I'll give you the gist of it here. So OO has taught us that the world is really a collection of objects. Everything in the world is an object, right? And we can describe these objects by types. And so a chair is an object, and we have a type that describes all kinds of chairs, or butt supporters, if you want to use the technical term here. OO also allows us to associate methods with data. So everything you can do with or to a chair is collected in one place by this type. And that's very convenient, right? It gives us a nice logical structure for anything chair-related. So in OO, we often end up with classes like this. I know this is totally made up, but hear me out. It covers a lot of different scenarios, and you can use the same class in a lot of different contexts without changing anything. That's a very powerful abstraction right there. But unfortunately, being a jack of all trades means that sometimes you're really a master of none. So what's the cost of all this flexibility? Let's say, for the sake of argument, that what we want to do with the class this time around is we want to calculate the sum of those values if the red, green, and blue flags are true. This can clearly be handled by our class, right? The straightforward implementation is we run through all the objects, we check the flags, and we do the summing. It's completely straightforward. Under the hood, of course, we know that this is a class, so the different instances are allocated on the heap. The array itself is also a class, so it's also on the heap. And it doesn't contain the data, it just contains references, right? So in order to run through all the objects, we have to follow those in directions. The objects might be all over the heap, so we might not get super great locality. So we have to follow references and traverse the heap, and this might hurt performance, right? So, hey, let's make it a struct, right? If we make it a struct, everything is nice. Now, all of the data is stored inline in the array, so we avoid the indirection. And presumably, the data will also be local, right? There will just be in contiguous memory, and it will be awesome. So how much faster does this make things? Well, it helps. But not a whole lot. In this case, the best case is just shy of 10% better. That's, 10% is great. I'll take that any day. But maybe it's not really worth celebrating, and we shouldn't, bring out the champagne and declare victory. So what's the issue here? Well, even though the instances are stored in line, we only use a fraction of the data from each instance. So we're blowing through these cache lines again, trying to collect useful bits for each instance, right? We end up reading a lot of data that we just throw away. We don't use it, so we get a lot more memory reads than we need to. And that hurts performance a lot. So if we look for this particular task that we're trying to do, what kind of data from this class do we actually need? We only really need a few fields here, right? We need the float values, obviously, and we have the flags that tell us whether we should do something with those values or not. If we can pre-process the data, we can just store the values in 3 different arrays, one for the reds, and one for the greens, and one for the blues. That's as simple as it gets in this case. Our code doesn't change much, right? It's still just going through these structures and doing some symbol calculations. And since, in this case, we pre-process the data, we can actually just skip the whole branching part of it. Now, in this case, for this particular case, I'm not saying you should do this all the time, but in this case, benchmark.net shows us that we can do the same exact calculation 7 times faster. So if this calculation is important to our application, picking just the data we need for the operation can be a huge time saver. So every abstraction comes at a cost, right? If we want to optimize performance, we're better sticking with simple, compact data structures that will get the job done. Water time. So suppose we have an array of integers and we want to populate another array with the absolute value of those integers. That involves obviously checking the value every time and figuring out if we need to drop the minus or not. That's a simple branch. There's a math.apps function in the library that you can use, but to keep it simple, I've rolled my own here. It's very simple, and I've highlighted the branch so you can see, we're looking at x, and if we need to flip the sign or just return x. Now, we can run this code, obviously, against different sets of data, and let's see what that does. The graph here shows that depending on the frequency of negative numbers in our data set, the runtime changes quite a lot. On the top, we have a data set that only has 1% negative numbers. Then we have, in the middle, we have the 50-50, so half of the numbers are negative and the half is positive. And at the bottom, 99% of the numbers are negative. There's a 5x difference between the best case and the worst case here. So if the values are mostly negative or positive, the code completes much, much faster. And it would be nice if we can do something to avoid this difference in performance. So branch prediction in its symbols form really works like this. If we've seen a lot of ducks already, the next thing is probably going to be a duck. And the same thing, this explains why the distribution of 50-50 performs so badly, because every time we see a number, we try to figure out what's the next number, and if the numbers constantly change, we get a lot of incorrect guesses. On the other hand, when we have the distribution with just a few positive or negative numbers, we get a lot more correct guesses, and that speeds up things quite significantly. So one way to help range prediction in this case is to sort the data. If we sort the data, we have all the negative numbers on one end and all the positive numbers on another end. So there's only really one switch, like we see ducks, and then we see something else. Let's see how much that actually matters. We can see that by sorting the data, we get really good performance, but more importantly, we get consistent performance across the different distributions. Now, I know what you're thinking, sorting the data takes time as well, so that might not always be a good option either, right? Is there anything else we can do? Well, in some cases, we can rewrite code to avoid branching. In this code, I've done the same function, but instead of using branching, I'm just using bit shuffling. It turns out that the code here is actually a little bit more complex, but we don't get any mispredictions at all. So how does this run? Slightly worse than the sorting part, because the code is a little bit more complex. But you'll see that the runtime is still pretty uniform across the data sets, and it's still a lot better than what we had with the branching. So finally, let's explore one more option. .NET Core has made a lot of great perf improvements. Excuse me. And one of the things is that we now have access to SIMD instructions or vectorizations. SIMD allows us to execute the same instruction on several data elements at once. So instead of getting the absolute value for just one integer, we can get it for a number of integers with just one instruction. And the number of instructions it can handle in parallel depends on both the CPU and the data type in question. So basically, your code has to ask the hardware, hey, what can you do? So here's a SIMD implementation of getting the absolute values from an array. First, we ask vector of int, what capacity, how many numbers can you actually handle? And we get that from the count property here. And then we run through the data in chunks of how much that capacity is, right? This is the number of data that we're handling at a time. We use the new span of t to create a small span of this array so we don't create a new, allocating in this type loop would be horrible, right? So span of t allows us to say, hey, just look at these few elements. We feed that to the vector version of the apps method, and then finally we copy the result to an output array. Let's see how well this does. So you can see here that we have pretty much the same runtime across the different distributions, and the best case scenario is 10 times faster than our baseline. If you can use SIMD, you should, because it rocks, right? This is a great option in these cases. So branching adds overhead, because it reduces the benefit of pipelining. And the more you can help the CPU pick the correct branches, the faster your code will run. If your problem can be solved with SIMD, do it. OK. Last, let's look at the parallelism. We know that by utilizing multiple CPUs, we can reduce the time needed to complete certain tasks. Ideally, in the perfect world, we would like to see the time reduced in proportion to the number of CPUs we're using to solve the task. So with 2 cores, hopefully we can get it done in half the time. With 4 cores, a quarter of the time, and so forth. Here's a simple task that can be parallelized. We want to calculate the sum of a lot of roots. Finding the roots can all be parallelized because these are all independent tasks. So we can parallelize that as much as possible. And once we have all the roots, we just sum them. Here's a simple single-threaded solution to look at. This is our reference point, right? Remember, we're trying to make something faster by using parallelism. So we need to have something to compare against. This is it. So we can make it parallel, right? The simplest way to do this is to use the parallel features of the .NET framework. Parallel.For will run a number of concurrent invocations of an action. So all you have to do is tell it how many invocations do you want and what is the code you want it to run. And then the framework will handle the rest. So here's our first attempt. It turns out our loop into a parallel loop, and it's really simple. We have to let each invocation know what part of the input we should handle, and then the framework will just handle the rest. Let's look at that and compare it to a baseline. It's significantly faster. That's great. But I'm sure some of you know that there's a problem here, right? It's utterly broken. So it doesn't help us a lot. I mean, we have multiple concurrent invocations all hammering on the same data. That's not going to work. Now, if you don't care about correctness, this is still not a great option because we can do even better in that case. So, you know, this is just not good. Let's make sure that the result is correct, right, before we do anything else. We know that in order to make it correct, we can just make sure that no invocation access the result variable at the same time as another invocation. We can use the lock keyword to do that. This guarantees that only one invocation will ever only touch this result at a time. So the code is now correct, which is great. But now it's terrible, right? Not only is it significantly worse than our baseline, so it's horrible, but in fact, the more CPUs we throw after this, the worse it gets. And the reason is the same reason when you go to the bakers and there's a long line. Like the more people trying to get into the bakers, the longer you have to wait. It's the same thing here. All the threads will just queue up and wait to get access to this one variable. This is not going to work very well. It turns out that this multi-threading stuff is a lot harder than anticipated, right? Okay, so lock-free. The problem is locking is that all our invocations are accessing the same variable. So let's not do that. Let's give them separate variables, right? Let's have an array that says, you know, this index is for you, this index is for you, and this index is for you. Then we don't have any sharing, right? I mean, they all have their own little portion of this array that they can feed their result into. So here, here we will. You see the loop, we write to a specific index in the array and store the result there. And once we have all the result, we will run through that and calculate the final result, and we'll return that. Now, this is a huge improvement. Not only is it correct, but it speeds up things. But we're not getting anywhere to where we would like to be, right? If you look at the 8-core version, we're only getting about a 25% speed up here. That's a lot of battery use for a very little improvement. And I'm sure some of you have figured it out by now. It turns out that it's our friend the cache lines again, right? From C#'s point of view, we don't have any sharing, right? We are writing to separate indexes in an array. It's all fine and dandy, and there's actually nothing wrong here. We will get the correct result. C# and the CPU make sure that happens because we're not sharing anything. The hardware, on the other hand, sees things differently, right? It says you're never ever reading or writing one value. You're always doing these bulk operations. So it has to go and do all that work behind the scenes to make sure that we have a consistent view. And that adds a lot of overhead. This is known as false sharing, and it can really hurt the performance of your code. So, final attempt here. The best way to isolate data is just to make sure that we have it local to the thread. And this is what our last implementation does. Now we just, you know, we create a local variable. This will be on the stack of each of the threads, and it's never shared. There's no reason to log around it at all. And during the loop, each thread will only write to a local variable, completely safe. Once the main loop is done, we'll just copy that to that array we just created before, just for convenience. And finally, we will do the sum. But this only happens at the end, right? There's no concurrency going on here. We already calculated everything, so this is fine. And now, we avoid the overhead. And we see the expected improvements. With 2 threads, we spend half the time. 4 threads, quarter of the time. And 8 threads, we actually run 8 times faster than our baseline. So this is hard, but we can get a lot of power done here. So language semantics and hardware semantics can be different. And unfortunately, the hardware gets the last word here. So you have to keep that in mind. It doesn't matter what your language tells you. You have to take the hardware into account. Everything we've looked at today only applies to CPU-bound problems. If your code is I/O bound, or if it's GPU bound, or bound by some other resource, you have to address that first and in a different way, but that's an entirely different talk. However, regardless of where the problem is, there are some things that you can do that kind of always work. Plan for performance. Understand your key scenarios. What is it that's important to you? What is it you need to make fast? And think about what kind of capacity you want to run. It's very different if you have 100 operations or if you have 1 billion operations. Run performance tests. Code is super hard. And even the simplified CPU that I showed you today, it gets tricky, right? Real CPUs are a lot more complex than this. So it's hard. And prefer simple code. I love Link and all the fancy features of C# these days, but it can be much harder to reason about the code if you write that. You saw all of my code looked like code from the 70s, right? For loops and arrays. It's not really making the best of C#, but it's easy to understand and easy to reason about. And measure performance. Don't guess. Eric Lippert has this great blog post about if you want to know which horse is fastest, race them. There's an easy way to figure out which horse is fastest. You should do the same thing. And then use real data and collect data from the wild as well. Even if you do all your internal perf testing and you get the results, things might be slightly different in the real world. So you should have telemetry that tells you, how is my code running in the real world? Maybe there's a problem I don't test for. So do that. This is hard. Well, I think it's hard. You might be a lot smarter than me, so you know this already. But this is a talk about what I learned, so there you go. Anyway, if you want to know more about this, there are good talks and good blog posts, and there are books. This, the .NET Performance link that Adam Sitnik runs has a super long list of everything. So that's very useful. There are a couple of books that are kind of specific to both game engine architecture and data-oriented design, if you're interested in that. But just keep reading about this, because the more you read, the more you'll understand about performance. And with that, thank you for listening. I hope this was useful. I would love to hear your perf stories, so if you have time, feel free to bother me and chat to me about performance. I'd love to hear it. Thank you.